Good morning, everybody. Welcome to a wintry morning of Chem 1105 in April. And welcome from your host, me, Dr. White. I hope you enjoyed spring and summer. We lost that. I just zoomed and we're back in winter now in April. If you look at my lawn outside my house, there's snow on there. And it's April 17th. Boy, by the way, years ago when I was in college, that's a long time ago, on April 14th of that year, a long time ago, in the Chicagoland area, we had a monster snowstorm in April, and we had close to 15 inches of snow. The next day, it all melted, and there are floods everywhere. And because of that, the snow and the melting, the Internal Revenue Service, IRS, for the Chicagoland area extended the due date from April 15th to the 16th. Oh, good news. Last week I got my taxes in. All right, now on a more personal note, last Wednesday, I did not have my Zoom meeting lecture because I had serious medical problems. I was actually hospitalized. Good news, I'm still alive. But anyway, say a prayer for Dr. White, it won't hurt. But because of that, we missed Wednesday last week, and I didn't have a video. I put out this email. I sent out a quick one. Well, anyways, I put out this email that you should be looking at these two YouTube videos from a previous 1105 course I taught on Zoom. I will be assuming you have watched these videos. Now, something I did yesterday, if you notice, I have a video posted for 2023 14 12. That's the one I missed last Wednesday. Now, if you look at the time, it's only 2 minutes and 11 seconds. Why is that? Because in this video, I have, once again, the two videos that you should watch starting at the various times. I will assume that you have watched these videos, and just like most of you are watching this video, learn the material. That will be on test number 3. Now, today's game plan, before I have another announcement, I'm going to go through chapter 6 problem set, and then we'll continue with chapter 5, part 2, I think it's 5.5, solutions. Part of that I'm going to go through real quick because it's in those videos you should be watching. All right, the other announcement I have to make is I sent out this morning this announcement or an email, and it's this announcement. So you should see this, that when I looked at yesterday, the syllabus, I said, oh no, this week, Wednesday, I have a test scheduled, test 3. Well, I haven't finished everything. And that's why I have in my syllabus tentative test schedule. Because if I have to change it so you can do better on a test, I do. And I did. So pay attention. I am postponing test number 3 by 1 week. Test number 3 will not be given this Wednesday, the 19th. It will be given on April 26th at 12 p.m., right after that class and lab, or the class. I will send out an email with the password to open up test number 3 PDF file, and you'll have until Thursday, the next day, to take test number 3 and upload your answers as a single PDF file. All right, another thing I want to talk about, I just snuck a look at my clock, see how we're doing. We're doing good. All right, another thing I want to remind you. A while ago, I sent out a test amnesty email, and you have until the 25th of April to hand in any past labs and only take off 1 late point for any late points. I'll put out an email later today or tomorrow, but an announcement for late labs, besides uploading it, remember you have to do it as a single PDF file, besides uploading it as a single PDF file, you should email me so I know to go back and look at that, because I'm not going to go through every day and check Blackboard assignments. Who do I have to grade? That's a tremendous amount of work. You make my life easier, which is a good thing. The doctor told me I should drink a lot more water. And so if you see me drinking water more during my lecture, that's why. But anyways, make sure you send me an email what past labs you just uploaded so I can grade them and you can get your scores. And with that, I think I'm done with the announcements for now. Let's get to work. All right, let's look at Chapter 6, practice problems. But before we do that, I better open something up. All right, let's look at the following problems. And you should know how to do these as you learn. This is why I call them practice problems, because they help you for the next test. Oh, I gave that away. But anyways, let's get going. How many torr is 41.5 millimeters of mercury? What are we trying to find? Torr. Remember, torr is a unit for pressure measurement of gases. And mmHg, millimeters of mercury, is also a unit of pressure for gases. So we're trying to find how many torr. We're given how many milliliters. We start here, millimeters of mercury, and we're trying to get to torr. Use your good buddy, your good friend, unit analysis, and put torr on top of this ratio, millimeters of mercury underneath. Where do you get this? Oh, wait a minute. You look at important information, test number 3. And you'll see here I have 760 torr equals 760 millimeters of mercury equal 1 atm is atmosphere, which means 1 torr equals 1 millimeter of mercury. So I can go back 1 torr, 1 millimeter of mercury. Now those 760, 761, or the 1 torr per 1 millimeter of mercury are exact numbers. Therefore, when you do a multiplication division, you get the same number of significant figures in your answer that the number that you're multiplying and dividing by that has the fewest significant figures. Well, 41.5, 3 significant figures, the 1 exact numbers. So I get 41.5. Now, let's look at number 3. How many ATM is 741 torr? ATM is the abbreviation for atmospheres. That is a unit of pressure. So is torr. And notice I have note here, but if we look at important information, 760 torr equals 760 millimeter mercury equal 1 atmosphere. Therefore, for number 3, I have 741 torr. I'm trying to go to atmospheres. Time again to use your good buddy. Oh, I didn't do it. Time again to use your good buddy, your good friend, unit analysis. And whatever we're trying to get to, the atmospheres goes on top of this ratio. Whatever we're trying to get rid of goes underneath. And where do we get those numbers? 1 atmosphere equals 760 torr. Now the 1 and the 760 torr are exact numbers. If I do the math, I have to round off what's on my calculator. You know how this gives a ton of numbers, a lot of numbers. And 741, 3 significant figures. 1 and 760, exact numbers. Therefore, the answer should be rounded off to 3 significant figures. Now I have 0.975. You might get 9.75 times 10 to the minus 1. And either way you write it, the answer this way or this way would be correct on my test. And as you all know, I'm this close to the person grading the test, me. All right, let's look at number 4. How many torr is 1.237 atmospheres? What are we trying to find? Torr. What are we given? Atmospheres. So we start here. We had some ratio. What unit do I want my answer to be? Torr. And again, use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get these numbers? Important information. Right here. Ooh, outlined in blue. Anyways, 760 torr equal 1 atmosphere. 760 torr per 1 atmosphere. Now, when you do the math, remember 760 and 1 are exact numbers. The only thing you use when you're multiplying and dividing, you get the same number of significant figures in your answer as the number you're multiplying and dividing that has the fewest significant figures. You do not use exact numbers to determine significant figures. Therefore, 1.237 ATM atmospheres, more water because of my doctor, told me so. Anyways, actually my cardiologist, I'm very blessed. I have a great cardiologist, Dr. Lupovich, at the North NCH group. He is so good. I'm probably alive because of him. Anyways, this has 4 significant figures. Ooh, get that last finger up. 4, exact number. Your answer should have 4, and it does. All right, let's move on. If a balloon has a pressure of 658 torr and a volume of 1.8 1.894 liters. What is the pressure of the balloon if the volume is increased to 5.133 liters? Well, what do? Well, notice this is a balloon. That means gas. We're talking about volume and pressure. That's all that's there. And if you look at, I just closed it. That was not right. If you look at important information, test number 3, we have Boyle's law. And Boyle's law is P1 times V1 equals P2 times V2. P1 is the initial pressure. V1 is the initial volume. P2 is the final pressure, the pressure after you change something. And V2 is the final volume, the volume after you change something. I like these hand signals. I don't think I'll do it anymore. But anyways, so you need to use Boyle's law. And here we have P1 times V1 equal P2 times V2. Now, what are we trying to find? The pressure after you change the volume, and that's P2. What are you given? The initial pressure, and that's P1, 658 torr. You're given the initial volume, 1.894 liters. That's V1. You're given the final volume. What happens after the volume is changed to the pressure? So that new volume is V2. And now we have this right here. We're solving for P2. The equation we're using is P1 times V1 equals P2 times V2. How do you solve for P2? Well, you want it alone on this own side. And let me show you how we do this again. And what are we looking for? Well, if you forgot, go back and we're trying to solve for P2. That's the advantage of doing this, writing what you're trying to find and what you're given. So we're trying to find for P2. So how do we get this alone on one side? You remember anything divided by itself equals the number 1. So if I want to get rid of V2, I'll divide by V2, because anything divided by itself is number 1, meaning it's gone. Whatever you do to one side, you have to do to the other. Otherwise, you're not going to get the right answer. It's wrong. You got to do whatever. I divide this side by V2, I have to divide that side by V2. Anything divided by itself is number 1. 1 times P2 equals P2, and the other side is P1 times V1 over V2. And I like to rewrite it. You don't have to, but I do. Good habits I don't change. And now I know to get P2, I have to multiply P1 times V1 and divide that by V2. And you'll see I did. Here's P2 equals P1 times V1 divided by V2. I have these, so I put them in. Now, before I pick up my calculator, this one, I'll check my units. And notice here, we have liters divided by liters. That means the units cancel out, come on, and I'm left with torr. And yay, torr is a pressure. Now, remember, multiplication division. You get the same number of significant figures as your answer as the number that has the lowest significant figures. Now, in this case, 3 significant figures, 4, 4. What's the lowest number? And time's up. Hopefully you pick 3, and you round your answer off to 242. Now, one of the things when I did this problem set, I didn't put it in scientific notation that I should have. If you have your calculator, which most of you have, this is also either one of these is correct. And that's how you do that. Oh, let's do another one. Let's do number 7. If a piston, like in your car, the pistons that go up and down, has a volume of 22.4 L, that's liters, and 12.34 atm, that's pressure. What's the volume of the piston when the pressure is reduced to 3.567? And what are you being asked to find? First of all, we've got a gas, and the only thing we're dealing with is pressure and volume. As soon as you see that 8 points, you should 8 points, you should know it's time to use Boyle's law. P1 times V1 equals P2 times V2. Maybe it won't be 8, maybe it'll be 10. And remember, P1 initial pressure, V1 initial volume. P2 final pressure after you make a change. V2 final volume after you make a change. And now we're trying to find what's the volume of the pressure of the piston after you make a change. V2. What are you given? The initial volume, 22.4 liters, P1. The initial, oh, wait, I got that wrong. The initial 22.4 liters is the volume, V1. The 12.34 atmospheres, the initial pressure, P1. And when the pressure is reduced to 3.567, that's P2. So we're trying to solve for V2. We want to get it alone on one side. Therefore, to get rid of the P2, we divide by it. Whatever you do to one side, you have to do the other. And I did. P2 times divided by P2 is number 1. 1 times V2 is V2. And this side is still the same. I now take this, rewrite it. You don't have to, but I do. V2 equal P1 times V1 divided by P2. And now I'll put in what is P1, V1, and P2. Now, before I pick up my calculator, I notice atmospheres divided by atmospheres cancel out. Anything divided by itself is number 1, meaning those units are gone. I'm left with L, liters. Yay, that's volume. And now I'll do my math. And here, remember, for multiplication division, you get the same number of significant figures in your answers, number that has the lowest significant figures, 4, 3 significant figures, 4 significant figure, lowest answer or lowest number of significant figures that you're multiplying, dividing by, and 3, so you round it off to 3. Now that's 77.5 liters, which is also 7.75 times 10 to the 1 liters. All right, let's look at number 10. If you burp, yep, burp. Nope, I didn't burp yet. Oh, that was an awful joke. I'm sorry. But anyways, if you burp 86.75 grams of CO2 gas at 545 millimeters of mercury and 34.6 degrees C, what's the volume of your burp? We're trying to find volume, B. If you look at this, oh, by the way, I would have written 15 points there. If you look at this, nothing is changing. You have a weight, a pressure, a temperature, and you're asked to find a volume. And what do? You look at important information, test number 3, and that's the ideal gas law. And the ideal gas law is PV equal nRT. Now, it's important to remember, you have to use the right units for PV equal nRT. Get the right answer. And here, pressure is in atmospheres. Volume is in liters. N is the number of moles. Temperature is in Kelvin. And R, for the universal gas law, for this class, listen, for this class, you should use the volume of R as 0.821 atmospheres liters mole K. Now, R can be many significant figures. The number I use has 3 significant figures. This is not a definition. It's a calculated number. So now we have to go back and look at our problem. The biggest mistake students make on using PV equal nRT, they don't convert pressure, volume, temperature into the proper units. Now, while we're here, notice I have here important information, test number 3. Kelvin equals degrees C plus 273. So you didn't have to memorize it, but you do have to know when to use it. All right, so we want to use PV equal nRT. We're given a volume, we're given a weight, mmHg is millimeters of mercury of pressure, degrees C is the temperature. And I rewrote R as 0.0821 atmospheres liters mole K. So now we'll use PV equal nRT. We want to solve for V. We need to get that alone on one side. Therefore, to get rid of P, I'll divide by P, pressure. Whatever I do to one side, I have to do to the other. And I did. So anything divided by itself is number 1. You're left with V, volume, equal nRT divided by P. However, the pressure has to be in atmospheres. To go from millimeters of mercury to atmospheres, use a ratio. Use your good buddy, your good friend, unit analysis. Whatever you get, trying to get to goes on top of the ratio, atmospheres. Whatever you're trying to get rid of goes underneath, millimeters of mercury. If you go to important information, 760 millimeters of mercury equal 1 atmosphere. 760 millimeters of mercury equal 1 atmosphere. And now I know to put 1 atmosphere for 760 millimeters of mercury, as we did earlier this morning. These are exact numbers. This is the 3 significant figures. You get 3 significant figures. Now, this is one of those multi-part calculation problems. There are two ways of doing it. I'm a round off at each step person. You can also round off at the very end. And what I will do is calculate for test number 3. If there's a problem doing this, you can either round off at each step or at the very end. And if you notice at the bottom, I have both ways. If they're the same, that's what that means if you round off at the end or round off at each step like Dr. White. So we now have the pressure for putting into nRT divided by P. We need the temperature. That has to be in Kelvin. Oh no, we've got that in degrees C. And remember, from important information, test number 3, you are given degrees C plus 273 equal Kelvin. So what's degrees C? 34.6 degrees C. Add it to 273, and I get 307.6 Kelvin. Now, this is a little tricky. When you add, you get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest significant figures to the right of the decimal. In this case, 273 is an exact number. You don't use that for significant figures, multiplication, division, or addition. So notice this has 1 past the decimal. That's why the 0.6 is still there. And finally, N. N is, in case you forgot, moles, number of moles. Well, we've got grams. Oh no, you have to do what you learned for test 2. And that is, we have 86.75 grams of carbon dioxide, CO2. We want to get the moles of CO2. So if we have a ratio, whatever we're trying to get to, moles of CO2 go on top, the weight goes underneath. And where do you get that information? Well, in case you forgot, 1 mole of an element or compound is the molecular weight of that compound, and the molecular weight is the sum of all atomic weights. So 1 mole per the molecular weight of CO2. If you notice right over here, the sum of all atomic weights, 1 carbon at 12.0 on test 3. Just to remind you, like test 2, it will say, please use 3 significant figures for all calculated, for all atomic masses. I got into my all calculated, nope, wrong. Please use 3 significant figures for all atomic masses or weights. And carbon is 12.0. You got 2 oxygen. Oxygen is at 16.0. Do the math, add it up. It's 44.0. 1 mole of a compound equals the molecular weight, 44.0 grams. And now we'll do the math. I'll get a number. This is 4 significant. The 1 mole is the exact number. This is 3. My answer here is 3. And now I have N, 1.97. R is the universal gas law constant. And if you look at important information, test number 3 for the ideal gas law, I have that there. And Kelvin has to be in, or temperature has to be in Kelvin, and I have that there. Ooh, I'm doing good. And divide by atmospheres of pressure. Remember, pressure has to be in atmospheres. In case you forget, look at here. Important information, test number 3. It tells you. In the past, the students in my class would have to memorize all that, and they forgot. I have cut down on the memorization, but expect you to know how to apply this. In other words, learn the chemistry. And if I put in the numbers, notice moles cancel out, Kelvin cancel out, atmospheres cancel out. I'm left with liters, which is a volume. Yay! And remember, for this, you get the same number of significant figures in your answer as the number that you're multiplying and dividing. It has the lowest, 3, 3, 3, 4. 3 is the lowest. And I get this 69.4 liters. Now, since your lungs only hold about 6 liters or 5 liters of gas, this is obviously, I picked the wrong weight, but that would be one hell of a burp. You burp everything out of you. Ugh. But anyways, $69.4 can also be written, you'll see it on your calculator as this, 6.94 times 10 to the minus 1. Oh, let's do another one. Let's do number 11. If a tire contains 25.6 grams of nitrogen gas at 26 degrees C, 705 torr, what is the volume of the gas? The nitrogen gas in the tire. Well, how do we do this? Well, you look, we're given a volume, we're trying to find, well, not given, we're trying to find a volume. We're given a weight of nitrogen gas. We're given a pressure, that's what torr is, and we're given a temperature. Does anything change? No. So immediately, I just did it again. We look at the ideal gas law, PV equal nRT. P is pressure, V is volume, which we're trying to find, N is number of moles, T is temperature, and R is the universal gas law constant, 0.0821 atmospheres liters mole K. Remember, this only works if pressure is in atmospheres, volume is in liters, always give you it in liters. Moles, well, I'll give you weight, and you've got to do that conversion. And temperature, you'll always get in degrees C. I have never seen a thermometer or electronic thermometer called a thermocouple that's ever been in Kelvin. And R, you're also given. So we're trying to find volume. We're given a weight. We're given a pressure. We're given a temperature. I know to use PV equal nRT. Also, it's not on there. You'd be given 15 points. 15 points. And PV equal nRT is what we want to use. We're trying to solve for volume. Therefore, we want to get rid of pressure. To get rid of something that's multiplied times something else, you divide by it. So I divide by P, because anything divided by itself becomes the number 1. Whatever you do to one side, you have to do the other and divide that by P, and I did. And now I rewrite it, the volume, because P divided by P is number 1, 1 times V is V, equal nRT over P. Well, N is moles. We've got 25.67 moles, grams of nitrogen, and we want to go to moles of nitrogen. And where do you get the things you put on a ratio to convert it? Because remember, use your good buddy, your good friend, your analysis. The mole goes on top, whatever you're trying to get rid of, grams of nitrogen go underneath. And if we look at important information, test number 3, you'll see 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. Remember, use 3 significant figures for all atomic weights. And now, N is moles. We need the molecular weight of nitrogen gas. Uh-oh, a 2 fell off that N on the bottom. Don't look, don't look, don't look. But anyways, you have nitrogen gas, N2, 2 nitrogen. Each nitrogen atom has a atomic weight, the 3 significant figures, 14.0. And you get the molecular weight, number of moles per grams per 1 mole of nitrogen, 28.0. So I put that in there. And now I'll do the math. Notice grams of nitrogen divided by grams of nitrogen. Remember, the 2 fell off the second N. Cancel out. We're left with moles of nitrogen, which is what we want. 4 significant figures, 3. My answer is 3. Again, you can round off at each step like I do, or you can, let me try something different. Put this up here so I don't look like let's try, this is something I've never done before. I'm putting my, see there, right up there, the monitor that shows me right there so I don't have to look over here. Let's see how it works. All right, so that's how many moles. We need the pressure. Pressure should be in atmospheres. Oh no, we're given torr pressure. So I want to convert to atmospheres. I start here. I use my good buddy, my good friend, unit analysis to what goes in that ratio. Atmosphere goes on top. Torr goes underneath. And if we go to important information, test number 3, 760 torr equal 1 atmosphere. So here's what I'm starting with, trying to get the atmospheres. Whatever I'm trying to get to goes on top of the ratio. The torr, whatever I'm trying to get rid of, I don't want that my final answer, for pressure goes underneath. Anything divided by itself, torr divided by torr becomes number 1, gone. And now I do the math, and remember 705, 3 significant figures. The 1 and the 760 are exact numbers. So my answer should have 3 significant figures. Now, this is 0.982. Again, I guess I didn't have my calculator on scientific notation. And that's the number I could have had if I had my scientific notation after rounding off my calculator and scientific notation. And now I'll move on to temperature. Temperature is degrees C. It has to be in Kelvin for this to work. And therefore, how do I convert degrees C to Kelvin? Well, if you forgot, important information. Oops, too much. There we go. In blue, highlighted, Kelvin equal degrees C plus 273. So my temperature in Kelvin, degrees C, Celsius, plus 273 equals that. Remember, since 273 is an exact number and we're adding, 26 has 0 numbers to the right of decimal. My answer has that. Now I use PV equal nRT, V equal nRT over P, put an N, put an R, in case you forgot R. It's given right here, 0.0821 atmospheres liters mole K. And then temperature, 299, and pressure, this. And all the units cancel out. Moles of N2 divided by moles, that's gone. K Kelvin divided by Kelvin, that's gone. After I do that, all that's left on top is atmospheres liters. Below is atmospheres, they cancel out. I'm left with liters. And once again, if you round off at the very end or at each step, like Dr. White does, you get the same answer. And that would be 24.3 liters. And if your calculator was set to scientific notation, that would be your answer. And with that, it's time to take a break. I'm going to take a 5-minute break. I'll be right back, and we'll continue on. We'll get into the solutions chapter. See you in 5. Let's get going again. Good news. I just looked out my front window and most of the snow, I got frizzies today. Most of the snow is gone. There's still a little snow on my evergreen bushes in front of my house, but most of the snow is gone. All right. Let me do one thing. All right. Now, the next thing I'm going to cover is Chapter 5, Part 2. Now, as I put out an email last week and the videos you should have watched, I'm assuming you watched those videos. Now, I'm going to go through some of this super fast because it's in those videos that you should have been watching. And it's time for a new chapter and new material. New stuff. And this new stuff, Chapter 5, Part 2, deals with solutions. And you should know what is a solution. It's a mixture in one substance in which one substance is uniformly dispersed in another. Another way of saying that, homogeneous combination. Homogeneous means the same throughout, of two or more substances in which each substance retains its own chemical identity. If I mix water and salt, shake it up, you've got a solution of water and salt. If I take out, evaporate all the water, guess what? You'll get the salt back. And that's what we mean by each substance retains its own chemical identity. Now, important thing, solvent. That's the component of the solution that's present in the greatest amount. Remember, I'm going through at fast speed because this is in the videos I've subtle time, and know this, a solvent is the component present in the solution that is present in the solution in the greatest amount. All other components that are present in a small or smaller amount relative to the solvent are called the solute. Again, solvent, present in the greatest amount, the component, solute the others. And if we look at air, stuff you're breathing right now, this little squiggly means approximately 80 grams of nitrogen and approximately 20 grams of oxygen. Whoop, I forgot you don't read cursive. And the question is, air contains 80 grams of nitrogen and about 20 grams of oxygen. What is the solvent? What is the solute? Or if there are more than two components of solutes and air. Well, in this case, the solvent is the component present in the greatest amount. Nitrogen, 80 is greater than 20. Air is the solute. And that's how you do it. Look for the video to see other examples, the videos that I mention. All right. Now, there are different types. You can have gas, liquid, and solid. Now, water is a polar solvent, and it hydrogen bonds to molecules which have oxygen, nitrogen, and hydrogen. And water, hydrogen bonds to itself. And this helps in solubility. We'll talk about. Let me remind you, what's hydrogen bonding? Because the difference in electronegativity is a hydrogen and oxygen. Oxygen's more electronegative, wants to hold the electrons sharing between the hydrogen and oxygen together closer to itself. This means slight or little. It's lowercase delta in Greek. This is uppercase. This means slight difference, I should say. This just means delta, the capital delta difference. So there's a slight negative charge on oxygen, slight positive charge on hydrogen. Opposites attract, and that's your hydrogen bond, and you should know that. It's not a true chemical bond, but because of hydrogen bonding, water is a liquid at room temperature. If you look at molecules with similar molecular weights that don't, they're all gas. And alcohol is another example, ethanol, isopropanol. We'll learn more about that later in the semester. Now, I'm going to skip this part because you can see it in the video. Now, this is important. Oops, not in red. Did it again. And know this. And that's the rule of thumb. That's on this thumb today, but that was bad. That like dissolves like. What's the rule of thumb? It's something that's true most of the time, like 99% of the time. It's not a law. A law is always present, true 100% of the time. So like dissolves like is the rule of thumb, but it's quite an important one. And we'll talk more about it later when I teach you how does soap work. But anyways, like dissolves like means like solutes are soluble in like solvents. And that means polar solutes. There are two types of solutes and solvents. Polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. Now, what are polar? Water is the most polar substance around, and water can be both a solvent and a solute. Alcohols, like ethanol and drinking alcohol. I'm telling you should imbibe, or rubbing alcohol has isopropyl alcohol. Another one are most salts. Well, I really should say salts are polar, but a few salts don't follow like dissolves like, but sodium chloride does. And another one, sugar, is polar. Now, what are nonpolar substances in our daily life? Well, vegetable oil is nonpolar. Gasoline is nonpolar. Baby oil is nonpolar. And also, let's do Vaseline is nonpolar. So is nitrogen gas and oxygen gas. So the air you breathe is mostly nonpolar. Now, what like dissolves like means if I take water, I can dissolve salts in there. If I take water, I can put alcohol and sugar in there, and you'll get a homogeneous solution, the same throughout. Now, like dissolve like says polar things are soluble in polar substances, nonpolar things are soluble in nonpolar things. If you mix the two together, they're not soluble. You get separate layers. And if you take water and vegetable oil, they don't mix. And if you look on your screen right now, let me check to make sure you're seeing it. And you are. You see a bottle of Zesty Robust. I didn't know they had that type. I was familiar with the regular Italian dressing by Wishbone. That was one of my mother's favorite dressings. I make my own now. I don't buy Wishbone, but if you look here, there are two separate layers. On top, oil, this is an oil vinaigrette dressing. Vinegar is mainly water. And the top is the vegetable oil vinaigrette, and the bottom is the vinegar part, the vinaigrette with some seasonings. And that's two separate layers because polar water is not soluble in nonpolar vegetable oil. And you should be familiar with this chart. Hint. And if you take vegetable oil, it's soluble in Vaseline or Vaseline soluble in vegetable oil. Why you'd want to do that, don't know, but a number of years ago, I had a general chemistry. I was teaching at that time, 1211 at COD, and I taught this also like dissolves like I'm teaching this 1105 class. And a student of mine who was very sharp said, well, if that's true, Dr. White, like dissolves like, you take vegetable oil, is Vaseline soluble in it? I said, I've never done it. Next lab, I'll give you, if you don't mind, some vegetable oil and Vaseline, and you can, for the whole class, if you don't mind, because I don't like putting people on the spot uncomfortable, but he said, no problem. So let's see if it's soluble. I gave him in a lab some beaker of vegetable oil, some Vaseline, and with a spatula, he took some wet. Guess what? It was soluble, like dissolved like work. Now, watch the video for the type of problems I have here. I'm assuming you watched that video. And same thing with the electrolytes is in the video, and non-electrolytes. Now, let's talk about solubility. Solubility describes the solute amount of solute that can dissolve in a given solvent. And the solubility, this is stuff you should know. Huh, my pen tells me it's red and it wrote black. And that's the maximum amount of solute that will dissolve in a given amount of solvent under certain conditions. If you look here, I have Wikipedia. I think I mentioned before, but I'll mention again. When it comes to chemistry stuff, I don't know about other things, but chemistry, Wikipedia is spot on. For many years, I and other chemists who have the credentials, and I have, you see something wrong, we ask for it to be changed, and they do. If you look on the right hand, scroll down, we're talking about sodium chloride, table salt, the regular salt, table salt. If you scroll right down, you see properties. And if you keep on looking, you'll see solubility in water. And it's 360 grams in 1,000 grams of pure water at 25 degrees C. At different temperatures, the solubility is different. Now, they have for an ammonia and methanol, which we'll never use in this class, the solubility grams per L is liter, 1,000 milliliters, but there's no temperature. That's why they need a clarification. And if we do this real quick, let's go up to the top. Sucrose is table sugar. You know, the white stuff you put on things you want sweet or put in your coffee or tea. If we look here, solubility, and they say about 2,000 grams per deciliter, which is 100 milliliters, I believe. It's been a while since I thought about DL, deciliter. Yep, I was right. 1 deciliter equals 1/10 of a liter. I've asked you to learn, which is 100 milliliters. So if you look at sucrose, table sugar, wow, it's much more soluble in water than salt. And that's solubility, which you should know. All right, now, there are different types of solutions. You should know this. And there's a saturated solution, dilute solution, concentrated solution, and aqueous solution. Now, and non-aqueous. Now, I'm zooming through this because it's in the video you should have watched in the link I did that I would have done last Wednesday if I hadn't had a health problem. Yeah, I did, unfortunately. Now, one thing I do want to point out for aqueous solution is a solution in which the water is the solvent. non-aqueous when the water is not the solvent. Now, you see for certain things I'll be teaching you later to indicate it's an aqueous solution, you'll see bracket, AQ, close bracket. And whenever you see that, and you should know this, that means you're dealing with an aqueous solution, which means water is the solvent. Like I said, I'm zooming through here. And what affects solubility, temperature, and other things? This you don't have to know. And again, I'll have the switches off for this slide, but temperature affects solubility. For most substances, when you heat something up, it's more soluble in a solvent. Not all, but most. Now, something that you may think is a solution, but it's not, is called the colloidal dispersion. And what's a colloidal dispersion? It's a dispersion of small particles of one substance in another substance, a mixture in which the materials do not dissolve, but are just spread out uniformly. Salt and water is actually dissolved. Now, instead of using solute and solvent, they use the term phase, dispersed phase for solute, if it were, but it's not. And the substance in a colloidal dispersion present in the greatest amount is called the dispersing medium. Now, this is important, which I better write down. Unlike solutions, colloidal dispersions disperse light through them. What it means is now colloids is short for colloidal dispersion. I shouldn't have used that. But anyways, you should know light does not pass through a colloidal dispersion. And now it's time for me to show off one of my flashlight collection. About a year ago, I got back into, I always liked flashlights when I was a little kid and still did all throughout my life. And about a year ago, I found out that there's a subreddit called flashlights, and it's amazing. And learned all about the new high-tech flashlights like this one. This is my favorite one. Here's another one of my favorite ones. And you can see a lot more up here. I'm going, as they say on that Reddit, you go down the rabbit hole, you get hooked. And what does, oh, by the way, this one, learned about it. There's this one gentleman in China, Hank Wang, and he makes the best flashlights, high-tech flashlights in the world. There are other companies, but these are Hank Wang, and they're not cheap, trust me. But these are amazing. Now, here I have to assume you had sugar in here. See the water light goes through? Assume my hand is a colloidal dispersion. Nope, light doesn't go through. So how do you know if you have a colloidal dispersion? Does light go through it? Or is it dispersed and you don't see any white light go through? By the way, my hand isn't a colloidal dispersion, but it was a quick demo. And you should know examples. Milk is a colloidal dispersion of protein and fat and water. Latex paint is latex in water. And don't try this at home. Your blood is a colloidal dispersion. It's got amino acids and proteins, and now I'm way beyond my level of expertise of blood, and other things in water. So you should know examples of colloidal dispersion. Another one I have down here, I don't have there, is mayonnaise is a colloidal dispersion. If you don't believe me, take a flashlight, hold it up to a bottle of mayonnaise, and it won't shine through unless the bottle or container is empty. But if it's got mayonnaise in there, it won't. All right, now, this is new stuff. How do chemists quantitatively describe solutions? If I were to ask you, go in the lab right now or go in your kitchen and make me a solution of water and sugar. And if I had two different students do that, would they be the same solution? No, it matters how much sugar you put in there. And one might be a lot sweeter than the other because there's more sugar in the water to form different solutions. Same solvent and solute, but different. So how do we standardize these? How do we measure, describe a solution with the same type of solvent and solute? And we use what's called concentration. And there are different ways of determining concentration. One is by percent concentration by mass or weight. I should have here by weight. One is percent concentration by volume. And the one in red, so you know that's important, is molarity. Now, let's look at percent concentration by mass. Switches off for this, click. But it's something that's useful for your daily life, the rest of your life. And that is percent mass equals mass of the solute, and that's divided by mass of the solution times 100. And you can do this for each solute. Now, remember, the mass of the solution is the mass of the solute or solutes plus the mass of the solvent. So what this tells you is the higher this number, the more that solute component is in that solvent. Now, one interesting place where you see this, and I'll tell you Dr. White's story now. All right, here's this. Oh, I clicked on something I didn't want to. When I first bought this house, first time I went out to mow the lawn on a Saturday morning about 8 o'clock, I went in my brand new lawnmower because I first house where I had to mow the lawn. And guess what? After about 2 minutes walking with the lawnmower, I was attacked with every mosquito in the northwest suburbs. It was awful. So I put my lawnmower away and said, I got to get a mosquito repellent. Well, I went to Walmart because that was close by. I don't only go there about 4 or 5 times a year. And there's the name brand, a spray. Or you can buy a pump. And they have the Walmart brand, which is called Repel. Now, the material, being an organic chemist, I know this, that is a mosquito repellent is called DEET. and I'll talk about more about DEET later in the semester. But that's an acronym for diethyl ethylene 2-amide. Let's look it up. I think I botched it. And then diethyl meta 2-amide. I don't know where they got 2 E's from, but anyways, that's the active ingredient in most 99% of the mosquito repellents. Well, I looked at the label and saw you get 2 of these, or actually when I bought it, it's a spray. Let's see if they have it. I don't even think they have it anymore. But anyways, the spray liquid and the off had 2% or roughly 0.2 or 2%, I forgot, DEET, and the Walmart had 4% or double. The Walmart had 20% more weight and it was a lot less expensive. And because I know percent concentration, and let's see if we can see the label here. It says 40% DEET. I don't think it's that much. Well, I was the liquid. It could be. And that 40% is percent concentration. So which one did I buy? A Walmart. And I went home, sprayed myself, and I was able to mow my lawn and not get eaten by every mosquito in Northwest Chicago suburbs. Yay, which is an important thing. That's where it went. So that's percent concentration. Again, switches off for the slide. It won't be on a test. Now, another way of doing percent concentration is by volume. And here the percent volume is the volume of the solute divided by the volume of the solution, the total volume, times 100. And the only place I can think of very quickly where you see percent volume is if you look at a bottle of wine, you'll have the percent alcohol by volume. And the higher the number, the higher the percent. They don't use proof on wine, they use percent volume. Again, click, switches up. And now for the most important one. And it's time for Dr. White to be subtle again. So I will. And know this, really big hint. If I had a dial how much you should know this that only went up to 10, I've just turned it up to 20. I stole that from the movie. This is Spinal Tap. It's a cult movie. You might want to watch it. It's very strange. But anyways, let's talk about molarity. Molarity of a solution, and molarity is abbreviated by capital M. The molarity of a solution is a ratio given the number of moles per cell of solute per liter of solution. And you should know this, molarity, and I don't know where that dot came from. Let me get rid of it. There, I got rid of it. Molarity equals moles of solute per 1 liter of solution. Wow, I even wrote on the slide. Very important. Know this. You should. So let's talk about something when we talk about volume, which I haven't. 1 liter equals 1,000 milliliters. 1 milliliter equals 1,000 milliliters. Therefore, if molarity is moles per liter, you can also write it as moles per 1,000 milliliters. And most of the time in a lab, you're not going to use liters for measurement. You're more accurate if you use milliliters. Therefore, you should know equals moles per 1,000 milliliters. That dot came back again. Oh no, I've got the dreaded dot virus. Now, as you know, this whole semester, I've cut down on overall memorization. And if you look at test number 3, important information, molarity. Molarity is moles of solute per 1,000 milliliters of solution. And usually don't put the term solution there. You just have moles of solute per 1,000 milliliters. And that's molarity. And once again, I'll be subtle. Remember, molarity, if I can spell it. Did I tell you Dr. White, me, was always the first down in a spelling bee? I probably still would be. So molarity is moles of solute per 1,000 milliliters. And you should know how do chemists show this? Like on a bottle when you have a solution. Here's how it does it. And the question is, what does this mean? And you see a 1.55 capital M NaCl. Molarity is abbreviated by capital M. So this is the molarity. And this means 1.55 moles sodium chloride per 1,000 milliliters. I keep on doing script. Don't ask me why. That's better. So molarity, moles of solute per 1,000 milliliters of solution. And when you see it written this way, the capital M tells you a number, capital M, and a chemical structure or formula tells you molarity. Let's do another one. And here we have, what does this mean? 3.8 times 10 squared, capital M, HCl. By the way, you'll learn in chapter 7, this is hydrochloric acid. And when you see capital M, That means molarity. Moles of solute per 1,000 milliliters. What's the solute? HCl. So what this means is 3.8 times 10 to the squared. This is molarity, capital M, moles of HCl per 1,000 milliliters. And let me be nice and share some fun. And what does this mean? What does 8.73 times 10 to the minus 2? Oop, I forgot something. Back up. Remember the first day of class, I told everybody I don't walk on water unless it's frozen. Even then I stay off. I do make mistakes, rare, but that was one. All right, let's go through this. What does 8.73 times 10 to the minus 2 capital M sugar mean? Your turn. But here's a hint, and another hint. What does that mean? Time's up. And the answer is capital M, molarity. I'll write it here so I don't have to. And that's equal to moles solute per 1,000 milliliters. What's the solute? Sugar. You can make sugar solutions, different molarity. And what does this mean? 8.73 times 10 to the minus 2 moles sugar per 1,000 milliliters. And let's do one more question. I've got time. And let's look at a new question. What does this mean? And what is the solvent of the solution? So if we look at this, what does this mean? Well, capital M, that's molarity. And I know that's 8.61 moles of potassium bromide, KBr, per 1,000 milliliters. Well, what's the solvent of the solution? And this tells me AQ means aqueous, and that means water is the solvent. So whenever you see a molarity written this way, and you see bracket AQ, close bracket, you know that's aqueous, and water is the solvent. If I look at the clock, we're just about out of time. We actually are. So I'm going to remind you, watch the videos that I would have done on April covering the material I would have done on April 13th. You can find that in this email and announcement that I put out. You don't want to go on Blackboard? You can watch the short video that I put for, I said the 13th, it really is the 12th, that I missed because I was in the hospital, unfortunately. One last thing. Let me remind you, the amnesty program for late labs ends April 25th. If you need any help, contact Dr. White, me, with my office hours, or email me if you need any help with any of the labs that you haven't turned in yet. I'll only take off 1 point. Instead of you getting 0, you can get up to 9 points. That's a big help for your final grade. And I'll see you tomorrow morning. Don't forget the lab we did last week is due tomorrow. With that, I'll say Gang Gesund. I'll say that to myself, Gang Gesund. I could use it. I'll say Gang Gesund, goodbye. Remember, Gang Gesund means go in health. Gang Gesund, goodbye. I stole that from Granny and the Beverly Hillbillies. Bye.